Welcome. Our previous video introduced the concept of indirect inference and walked through how to do it for the Rust bus engine model at a high level. In this video, I wanted to do a coding demonstration to show how you can do this in Julia, but we're going to keep things as simple as possible, and we're going to estimate the parameters of an ordinary least squares regression model. Now, you might be asking, how is that a structural model? But by now, I hope you understand that a linear regression model can be a structural model. And I wanted to start with something as simple as possible so that we can get a small win at a small scale and then use that as a kernel upon which to build something grander. I did want to start with a little bit of mathematical background before jumping straight into the code, because this is a little bit different than the simulated method of moments that we talked about earlier. So we have our OLS model. This is the same model that we used for the indirect inference demonstration. We've got two x's, and then we want to estimate the intercept, the slope coefficients on those two x's, and the variance of the unobservable epsilon, which we assume is normally distributed. And this is going to give us 7 moments that we can use in our indirect inference auxiliary model. We can get the average value of y, the average value of the x's, the variance of y, and then the pairwise covariances between y and the two x's and between the two x's. This should contain all of the information that would be required to identify each of these parameters if we think through econometrically how identification would operate. So this is going to be our vector of alpha, and these are just parameter values. These are just going to be numbers that we can compute from both the actual data and from simulated data. So what we're going to do is we're going to compute the alpha hat in our real data, and then for each guess of the parameter vector theta, we're going to simulate 10 data sets that look like the actual data, and the x's are going to be the same across all of these simulation replications, and that's because the x's we're actually going to use from the real data. What's going to be different is the epsilon and the y, because the y is a function of all of these parameters, these structural parameters that we're trying to estimate indirectly through these auxiliary moments. So then for each of these simulations, we compute our 7 moments from the prior slide, and then take the average across them. And then we just want to minimize the squared difference between the real data auxiliary moments and the simulated data auxiliary moments that have been averaged across the 10 data sets. And then if we did things correctly, we should get back our OLS estimates, because this is a very simple structural model where the binding function is very clear what it is. So the idea is that we've obtained these structural estimates indirectly by looking only at the moments that were in our auxiliary model. Let's go into the code now. And if you watched the video on the simulated method of moments walkthrough, this is going to look very similar. It's the exact same structural model, which is a linear regression with 2 x variables. We're using literally the exact same data generating process. And the main difference here is that we're going to write a function that's going to take as its input the y and the x, and it's going to compute these 7 moments that we talked about. So it's going to give me the average of the y, the average of the x's, and the covariance between y and each of the x's, and the covariance between the two x's, and the variance of y. And it looks like it's also just including the number 1 in here as well, because it's getting all of the dimension of x, which includes an intercept. So that's not going to hurt us, but it's also not going to help us. All right, so we have this auxiliary statistics matrix or function, and we can call that on the data. So y and x are the data. And then my objective function, I need to read in the auxiliary model's moments from the data. So I'm going to call that beta sub d. And then I need to read in the x's, because those are the data that I'm using in the simulation of my auxiliary model. And then I need the structural parameter guess, and then I need some number of replications. I've set this at a default of 1,000, but we can use fewer than that, and we will when we call the function later on. Line 21 is just unpacking the parameter vector. There's nothing special about that. Line 22 is initializing the matrix is going to store all of the auxiliary simulations. And then here again, I'm fixing the seed like I would in simulated method of moments. And then for each of these simulations, I'm computing the y variable from the structural model. And then I'm using that with the observed data on the x's to make my auxiliary model statistics, storing those in the appropriate column of the auxiliary simulation matrix. And then I'm taking the average across the simulations on line 28, and then taking the difference on line 29, and then the objective function value is just going to be the dot product between these. Here I have a good balance of the moments. So I have 7 moments and I have 4 parameters that I need to estimate. This isn't like the SMM demo that we did where we had to reweight the variance because we've got more balance in the number of moments here. So we can estimate this just like we would with the simulated method of moments. We give it some starting values. We could start this from good numbers here, or we could start it from uniform random numbers. And then this is just going to this is going to call the objective function. And here we're using 10 simulations instead of 1,000 just to speed things up. Everything else is the same as the other walkthrough that I did. And then at the bottom, we're just printing our results out. So let's run this and see what we get. We've got our starting values here, which were just a bunch of uniform 0 to 1 numbers. And each of these function calls took about, I don't know, half a second or so, maybe a quarter of a second. And in the end, this took about 4 seconds to estimate. We got an objective value that was very, very close to 0, and the gradient is very close to 0 as well. And then lo and behold, our true values and our estimated values match up quite well. And you'll notice that the estimate versus the OLS is slightly different, and that's because this is a different estimator than OLS, so it's not going to give exactly the same number in a given sample of data, but it is going to give something very close within the confidence interval around the estimate. So I hope you found that example illustrative and intuitive. You might be thinking that there's actually not that big of a difference between simulated method of moments and indirect inference. I could have used those same moments that we did for indirect inference as the moments that I was matching on for simulated method of moments. And that's where you really see that these two methods are actually closely linked. The main difference between the two is whether you're dealing directly with your structural model or if you're dealing with the auxiliary model. Now that we kind of have a handle on the basics of these simulation-based methods, I thought it would be useful to talk about some practical ways that you can improve the simulations. So in the next video, we're going to talk about variance reduction techniques when estimating these integrated likelihood functions like you would see in simulated maximum likelihood. And then in the final video of this mini-series, we'll talk a little bit about Bayesian estimation with Markov chain Monte Carlo.